So, hello everybody. Today we're doing a problem that appeared as T4 of the 2025 Chinese Physics Olympiad finals. So let's go through the question first. The question reads, Lagrange points are of great significance in space science research. Near these points, probes can stay for a long time with less fuel consumption, suitable for developing telescopes and space stations for continuous astronomical observations. And you might know what Lagrange points are. These are basically points in a system of gravitating masses, in a stably gravitating masses. Let's just say that there are two masses, for instance, so we've got two binary stars that are rotating about their center of mass. So if we've got m1 and m2 that are rotating about their common center of mass, then there are specific Lagrange points in the rotating reference frame around m1 and m2 where the net force vanishes, right? Lagrange points might be stable or unstable, and those Lagrange points which are stable, there we can station some probes that are space stations, right? Where we will require less fuel because we will need less work to be done against gravity. We will have less gravity that'll be pulling us because around that position, gravitational and centrifugal forces and other kinds of forces, they cancel out, and we essentially reach a sort of an equilibrium. So we'll require no fuel to stay there, right? We can just stay there for free. So those are Lagrange points, and they are of great significance in space science research. Masses of three celestial bodies S1, S2, and S3 are M1, M2, and M3 respectively. So this might be a three-body problem. We're going to have to read further. M3 is much smaller than M1 and M2. They're possibly asking us to ignore the gravitational effect of M3 on the two other masses. The influence of S3 on the high mass celestial bodies S1 and S2 can be ignored, exactly as we assumed. Assume S1 and S2 perform uniform circular motion around their center of mass O, and the distance between them is r. When the low mass celestial body S3 is at certain special points in space, it can remain stationary relative to S1 and S2, which basically is the definition of a Lagrange point. These points are called Lagrange points. Let the gravitational constant be g, that's the universal gravitational constant. We're defining two constants, alpha and beta, right? And if alpha is m2 over the total mass, then beta is just m1 over the total mass, right? From the definition that's given to us, right? So the questions ask us, find the angular velocity omega of S1 and S2 rotating around their center of mass O. This is just simple Newton's laws. Find the positions of all Lagrange points. This is the second problem. We might have to analyze a bit more than the first problem and the second problem. Analyze the stability of the equilibrium of S3, that is the space probe, at the Lagrange point that's closest to S2. Okay, so there we might have multiple Lagrange points. And consider the motion. So we're going to have to consider the dynamics of this S3, which is the space probe, near the Lagrange point closest to S2. Assume that the initial deviation in position and initial velocity of S3 can be controlled so that the mode in which its position deviation grows exponentially with time does not appear. Alright, so there are multiple modes of dynamics of S3 around this particular equilibrium point, which are considering closest to S2. And we're asked to find the expression for the change in S3's position with respect to time. So we're going to have to solve these differential dynamic equations that we're going to obtain via Newton's laws. And we're only keeping the first order terms of the deviation in our derivation. First order terms, as I think it's been given that alpha is very, very small as compared to 1. Only under these approximations are probably these questions analytically solvable, right? So in questions 2, 3, and 4, we assume that alpha is very, very much less than 1, meaning that beta is very, very close to 1. And find the conditions that the initial position and velocity should satisfy. Should satisfy for what? For the modes in which the position grows exponentially with time does not appear. So this is our condition, and we're going to have to find the conditions for initial position and velocity such that that is true. So we've done our preliminary reading of the problem, and that's the most important part, right? So we've understood everything that the question's asking us, and we're now going to delve into the analysis. So first, it is a very standard fact that the angular velocity of a binary star system is just given over by this particular expression. It's derived by Newton's laws. So basically use the definition of the center of mass to say that the deviations from the center of mass are related by this particular formula, right? M1, I've assumed the left mass, M2 is I've assumed the right mass. I've drawn a particular instant when they're rotating relative to the center of mass, right? And from these two equations, the second one coming from the constraint that the stars are always separated by a distance r, right? We can solve for the two distances from the center of mass. And once we have that, we use Newton's laws, right? The centripetal force for the circular motion in the space frame, right? In which the motion is circular for M1 and it's also circular for M2, right? The circular motion for M1 should be provided for by the gravitational force coming from M2, right? And that just allows us to derive omega. Or we could do it the other way as well, right? This centripetal force for M2 comes from the gravitational pull from M1, right? So we could do it the other way, and this expression is very standard and known. So part one, there's not much analysis to do in part one. We go for part two, right? So part two asks us to find all the positions of Lagrange points that exist, right? And when you're asking for Lagrange points, you're basically talking about the frame in which M1 and M2, they're both at rest. That is, we're talking about the rotating reference frame, right? This reference frame, it rotates about the z-axis with an angular velocity of omega, right? So that's the frame that we're talking about. And rather than making that the z-axis, I think it's more beneficial if we make this the z-axis. That'll give us a better picture of everything that's happening. So this is the xy plane, right? This is the xy plane where we're finding all the Lagrange points. As you'll see that all Lagrange points will lie in the xy plane. And about the z-axis, we're having a rotation of angular velocity given by this expression. Anyway, since we're working in the rotating reference frame, we're going to have to use the force transformations, right? So force in the rotating frame will have three additional terms, which we call the pseudo forces. First one being the centrifugal force, the second one being the Coriolis force, and the third one being the azimuthal force. When we're finding equilibrium points, right, we basically neglect the rotation, the change in the rotation angular velocity, right? Because omega is constant, by the way. Omega is constant. Those masses aren't changing. The distance between them isn't changing, right? So everything's constant, right? So g isn't changing. The sum of the masses isn't changing. The distance isn't changing. It's basically a perpetually rotating binary star system. Omega isn't changing, so we can neglect this term throughout the entirety of the problem, right? There's nothing that's going on regarding a changing omega, right? So the azimuthal term, that can be safely ignored. All right, so next, talking about the Coriolis term, since the Coriolis term includes the velocity in the rotating frame, this v that we're taking the cross product with omega, that's the velocity in the rotating frame for the probe, right? So because we're considering equilibrium points, that velocity is zero, so we can neglect the Coriolis term as well. And the lab frame forces, which are the gravitational forces, right? And the centrifugal forces are enough of a headache for us anyway, with just themselves. We don't even need to care about the rest two terms. Okay, so we're going to write the acceleration, which is basically this equation, everything divided by mass of the space probe, which I've considered to be small m. So that is going to be given by the gravitational pull, which I've symbolized by the g vector, minus the centrifugal acceleration, or need I say plus the centrifugal acceleration, right? So that is going to give me the acceleration in the rotating frame. Now moving on to write the dynamic equations and setting the acceleration in the rotating frame to 0, and that is going to give me solutions for this vector r, wherein I can put the probe so that the net force is zero. So G is going to be due to the two gravitating masses. So this is the gravitational pull due to M1, right? And this is the gravitational pull due to M2. So this is just Newton's law, right? This is just Newton's law. It's just G M1 divided by r squared, where r squared is the displacement. This is the displacement term, right? We're having a exponent of 3/2 because we're also including the vector for the position deviation, right, of the space probe, m, with respect to m1. So this is the vector that's relevant in writing the gravity equation. Something that's important to note here is that I've written a plus x1 for the left term and a negative x2 for the right term, right? Because I'm only considering the magnitude of x1. So x1 is at a negative x coordinate, so we're going to have to add that, right? And x2 is at a positive x coordinate, right? So I'm going to have to subtract that from any arbitrary point that I take. So because I'm just plugging in x1 as alpha r and x2 as beta r, right? So I'm going to have to use that small difference there. And I've written the net gravitational acceleration due to both the gravitating masses. For the centrifugal term, it's really easy. It's just going to be radially outwards, right? Radially outwards from the z-axis. And we all know what the formula is, right? It's just omega crossed with the vector omega cross r, augmented with a negative sign at the front. We carry out the cross products and it's just a simple result, right? We need not even carry out the cross products. We already know that that's what the centrifugal force is going to be. We set everything equal to 0 and we look for points x and y which satisfy this equation. We're going to have to equate the components first, right? We're going to have to equate the corresponding x and y components. So this is the particular equation that we're wishing to solve. So first, let's look for solutions which do not exist along the y-axis. If they do not exist the y-axis, we can equate the y components and we can cancel the y's, if you can see it directly from equation 2. We can cancel the y's, and we can only cancel the y's for y is not equal to 0 component. If we look for y equals 0 components, then equating the y components will yield nothing because y equals 0 will just cancel out everything and that equation won't even make sense, right? So we can only equate the y components for y is not equal to 0 solutions, and which if we do, we're going to get this. And we can replace that into the equation where we equate the x components. So we can equate the x components, right? And since we've already gotten this term, right, we can replace this particular thing with this, right, which we obtained from equation 3, equating the y components. We can replace that in the equation which we get by replacing the x components. So we do that, right? We're going to replace this particular term, which also appears in the x components. We can replace that, and we obtain this particular thing, equating the x components. With our equation for the x components, we keep on solving that, right? So if we analyze the omega squared x and the omega squared x terms in the LHS and the RHS cancel out. Also, the terms, but this particular term multiplied by x and this term that we already have at the front, they also cancel out, and all that's remaining is just this, right? And now we use the definition of omega that we obtained in the first part of the problem. Which is given by this, right? It's just g times the total mass divided by r cubed. So we use that in the equation, which we obtained by equating the x components. Once we use that definition for omega, we actually obtain this particular solution for x and y. So x and y need to satisfy this equation. And once we have that, we can again plug this back into equation 3, right? Which we obtained for the beta gravity term, right? And using that, we can again also obtain what this distance is. This distance relative to the beta r star, that is the second star, right? We can also obtain this particular distance. We basically need to solve for x and y. Right, so we basically need to solve for x and y which satisfy equations 4 and 5. X and y which satisfy equations 4 and 5. Which if we do, we're going to obtain two solutions for x. Two solutions for y and one solution for x, right? So if we equate equations 4 and 5, we can see that this and this, they have to be equal, right? They have to be equal. And if we equate that, if we take the positive and positive solutions, that yields nothing for x, that yields nonsense. We're going to have to take the other solution, which is the positive of this is the negative of that, and that yields a valid solution for x, right? And that valid solution for x, when plugged right back into either equation 4 or 5, that yields a valid solution. Valid solutions, for, as I should say, because there are two solutions for y. So we've already obtained two Lagrange points. One of them being x equals beta minus alpha, half of that times r, and y being at either plus or minus root of 3 over 2 times r. Okay, so we have two Lagrange points that we obtained thus far. Okay, and we're moving on to for more Lagrange points. Okay, so we're now considering the on-axis points for y equals 0. And as I said before, if we're looking for y equals 0, then we cannot equate the y components, right? Since equating the y components in the first equation for y equals 0 yields nothing. That yields nonsense. All the y's cancel out, and that equation yields nothing. So the equation that we got before by equating the y components, I think it's taking a bit of time to load, but the equation that we obtained, which allowed us to obtain all of this by equating the y components, right? The very equation that equated the y components from the first equation does not hold, right? It does not hold, which is exactly why we can only equate the x components. So this particular equation, which we got by equating the y components, this does not hold because all the y's just cancel out, right? If we plug in y equals 0, if you can see directly from the first equation for the y components, if we plug in y equals 0 because we're obtaining the on-axis points, right? This equation is already satisfied, right? This equation does not have to be true because all the y's are already 0, and so the y component equations are already satisfied. That equation 3 will not necessarily stand. So instead, we're going to have to deal with the x components. This is what we get if we equate the x components, and I think this is directly apparent from the first equation, right? We plug in the value of omega, and now we're going to have to solve for all roots of x for this equation, and that's pretty complicated. If you analyze this carefully, we've got an absolute value there, right? Once we have that absolute value, we're only taking the positive root of that, and because this might be negative, right? This might very well be negative. All right, this might very well be negative, or that might be positive, but we're taking an absolute value of that same thing in the denominator. And if we further move on to simplify everything, right, this is a cubic, we take the least common multiples of both sides, that becomes a 6th order or 7th order polynomial, and it just becomes really complicated. So like solving for the roots explicitly for this, finding all the values of x for the on-axis components, that is on the y-axis components, that's not really analytically possible. So I think that is exactly why they've given us the approximation that, alpha is like really small as compared to 1. Alpha is like really small as compared to 1. So so let's try non-dimensionalizing everything, right? So let's say that this particular thing is a particular scaled factor of r, right? X minus beta r is u of r, where u, we've chosen it as a certain variable that parametrizes x, right? To parametrize x, right? So because if we choose x minus beta r to be a certain scaled version of r, right, we can non-dimensionalize this equation as we'll see below, right? So once that non-dimensionalization is done, all right, if we assume x minus beta r to be u times r, Then we can also say something for x plus alpha r, which appears in the first term, right? We can also say something for x plus alpha r, since alpha is just 1 minus beta, yeah, and x minus beta r is already said to be ur. We can say that this thing becomes r times 1 plus u. So this thing becomes r times 1 plus u. And again, we're obtaining x plus alpha r as a certain scaled version of r itself, right? 1 plus u characterizing x in x plus alpha r. Anyways, after that non-dimensionalization is done, after we've non-dimensionalized this equation, we obtain something like this in terms of the dimensionless variable u. And further simplifying, we obtain something like this. And this is completely non-dimensional. Beta is just some ratio of the masses, m1 and m2. Alpha is just some ratio. Beta is again some ratio. U is a non-dimensional variable parametrizing x, right? And so there can be three cases for which we can solve the equation. Notice we've not used the approximation for alpha that's given, right? Not yet. We're going to do that soon. So so there can be three cases for this, right? So if x plus alpha r, that is the point that we're considering in the xy plane, right, is greater than 0, and x minus beta r is also greater than 0. That is, we're considering points that are, you know, very, very to the right, very, very rightwards, right? If we're considering that particular region where everything is just, you know, positive, then that means that this and this, both of them, they're positive, right? That means that 1 plus u is also positive by the definition of what u is, you know. 1 plus u is also positive. And u is also positive, right? So both of them will be positive in that scenario. If we consider another case where x plus alpha r is positive, right? X plus alpha r is positive, but then x minus beta r is negative, right? So that is a very valid case, right? You add something to x that might be positive, but then you subtract something from x, and it's a substantial value, by the way, because beta is very close to 1 as given in the approximation, right? It's a very substantial value that you're subtracting. This is a very possible case, right? What is not possible is x plus alpha r being smaller than 0 and x minus beta r being larger than 0, right? This is not a possible case because this is not a possible case because adding something giving you less than 0 but subtracting something giving you greater than 0, that's not a possible case. So that's the only non-possible case, right? Another possible case is that both of them, they're smaller than 0, right? And in that case, 1 plus u is smaller than 0, yeah, right? Because, you know, x plus alpha r is said to be 1 plus u times r, and u is also smaller than 0. So that can be another case. So we have three cases for which we can put, for which we can use, because this term might be positive or negative, and this term might be positive or negative, right? So you can use three different combination of constants of 1 and negative 1 in front of the terms, the left hand side terms in equation 8, if we wish to solve them, that is, right? So let's add in s1 and s2 in front of the terms in equation 8, right? In the first case, both are unity, both are plus, right? S1 and S2, they're both plus 1, right? Because because 1 plus u and u, they're all both greater than 0, right? They just become u and they cancel out with the term below, right? And in the same equation, right, cancelling the numerator and the denominator will require us to know the sign of what 1 plus u and u respectively are. And so for the second case, s1 is 1 and s2 is negative 1, right? That's what we're going to have to plug in into the second term if we want to cancel u and, I'm sorry, if we want to cancel u and u cubed there, it will be a squared, but we'll need to plug in the signs carefully, right? Is it a plus or is it a negative sign that we're going to have to use in front of the second term? So that's another thing. That's another thing, yeah, right? We're basically characterizing the signs that are to be used by unity and negative unity by S1 and S2, right? For the three different cases, right? And for the third case, as is very apparent, for the third case, S1 and S2, they're both supposed to be negative. That's for the third case. So what we're now going to do is we are going to try to solve for u, right? And here is where the approximation that alpha is very, very small as compared to 1 comes in, right? So let's try to express beta in terms of alpha, and you know that beta is 1 minus alpha, and separate the equation such that we can factor out alpha from all of the terms which contain alpha, right? So we've written it in this particular format. We've simplified this equation, right? Writing beta as 1 minus alpha because that's already given, right? Beta is 1 minus alpha, and then we consider all the terms that contain alpha, and we factor alpha out of all of them. We write that in the LHS, and everything that remains, we write that in the RHS, right? So let's try to plug in the cases one by one, right? We've not used the approximation that alpha is very, very small as compared to 1 yet. We've not yet employed that. But we're soon going to see why we've written it like this instead of, explicitly solving this very high order polynomial for u, because we cannot do that analytically, right? That's not feasible. Even our calculators only apply for a cubic or at max a biquadratic equation, right? So we've collected the terms with alpha, with a factor of alpha in them, and written that in the LHS, and everything else we've written that in the RHS. So for the first case, S1 and S2, both of them, we're supposed to plug in 1 for both of them, and we do that, and we need to notice something. Consider what happens when you let alpha approach 0, right? If alpha approaches 0, you can see that in the LHS, u also needs to approach 0. U also needs to approach 0. So you plug in 0 in this term, you plug in 0 in this term, you see that this whole thing goes to 0, right? So that's what you need to notice. So that means that you can expand this particular equation near the values of alpha naught and u naught, right? So if alpha naught, if for alpha equals 0, u equals 0 too, then for a small deviation for alpha, this equation needs to be satisfied, where u is also a small deviation from u naught, right? And we consider only the first order terms in delta u, right? Considering only the first order terms in delta u, because also delta alpha is also small, right? We consider only that, then we can obtain this small change in u, that is delta u. The small change in u is also the value of u, because u naught is 0. The point where we're expanding for u is 0. We can obtain the value of u as a function of alpha, right? And the small deviation is alpha is also the value of alpha, because where we started from is 0 in the first place, right? So once we have the value of u with relative to alpha, with respect to alpha, then we can find x, because x we parameterized in terms of u. So once we have x, right, x is beta plus u whole times r, but beta is 1 minus alpha, and we're only asked to keep the leading order terms, right? Alpha is very small. That means alpha over 3, which is also in the order of alpha, reduced by 1 by 3. The order is reduced by 1 over 3. The negative order is reduced by 1 over 3, means that alpha by 3 to the power of 1 by 3 is very, very large as compared to just alpha. So we can safely ignore this term, right? So imagine alpha is something like 10 to the power negative 12 or something, right? So when you take the third factor of it, when you factor it down by 3, you get something like an order of 10 to the power of negative 4, right? So this becomes very, very large as compared to just alpha, so we can safely ignore that term. And we obtain something like this for the solution for the Lagrange point solution. For the case where S1 and S2, they're both 1 for the first particular case, this case, right? So we've actually obtained the Lagrange point that the first case represents in the first case. So let's try to consider the second case now, and we're going to repeat the process actually. We're going to repeat everything that we did for the second case, right? So this is the equation that we get for the second case. By plugging in S1 to be -1, sorry, S1 to be 1 and S2 to be -1. So that's the case for that's the thing for case 2. And even here we shall notice that as alpha approaches 0, u approaches 0. So we again expand near alpha and u both being 0, right? So expanding again in first order, we obtain something like this, and this time it's just almost identical to what we obtained previously, the only difference being we obtain a small negative sign. So since we're expanding near both of them having the original value of 0, the expanded deviations are the values themselves, and u we can solve in terms of alpha like this. And again, since x is beta plus u times r, and we can safely ignore the term alpha because that's way many orders smaller than alpha raised to the 1 over 3, we can write yet another Lagrange point. Okay. And now comes the case where we consider both of them to be negative, right? So 1 plus u is negative and u is negative. So we're considering points very far off to the left, right? Very far off to the left, such that this is what our equation reduces to. This is what our equation reduces to, right? So we've got everything out of which alpha can be factored out to the left and everything else to the right. Okay, so this time something's different. Notice that as alpha approaches 0, this gives two valid solutions for u, right? If this term approaches 0 from in the LHS, then either the first factor of u squared can approach 0, right? That's one possibility, or this whole thing can approach 0, for which obviously u has to go to -2, right? So consider the u equals -2 solution first, right? So we're going to expand this whole thing near u equals -2 and alpha equals 0. And when we do that, when we do the expansion, we consider only the leading order terms, after binomially expanding everything, we obtain something like this. And I hope you go through the steps and consider exactly what I've done there. Consider exactly the things what I've done. For example, for this particular thing, I've written u as -2 plus del u, right? I've written -2 plus del u, and with -2 plus del u, this just becomes 1 minus 2 times del u, because 2 comes to the front, when we binomially expand that and neglect higher orders of the deviations in u, right? And for the second term, u squared, I've basically written as -2 plus del u whole squared, and that's just identical as del u minus 2, right? I factored 2 out, and since after you factor 2 out, you obtain something like del u divided by a factor of 2 in the right term for this particular factor. Then this exponent comes in front of the second term when you binomially expand, and you obtain something like this, right? So basically that's the whole process. I do that for every single term. I do that in the RHS as well. And after some simplifications, after some neglecting of the higher order terms of del u and del alpha, right? There are no higher order terms of del alpha, by the way. You obtain something like this, right? That del alpha, 7 times del alpha is 12 times del u. I know that these are, weird numbers for something that's, so rooted in our universe, 7 and 12 being obtained as, factors of a valid Lagrange point, that is definitely weird, but that is a very real thing. And since delta u is not expanded out of u naught equals 0, it's not u naught equals 0 this time, it's actually u naught equals negative 2. So u has to be written as negative 2, negative 2 plus that expanded term, right, which happens to be 7 over 12 from this particular equation. 7 over 12 times alpha. And alpha is definitely expanded from 0, right? We're considering only small deviations in alpha. And since x is known as beta plus u times r, beta is just 1 minus alpha, we can write the solution for x, right? So we've obtained three particular solutions for the on-axis points. So this is one of those. This is the other. And even above, this is the third one, right? So we obtained three particular solutions for Lagrange points lying on the y-axis. So I've drawn a diagram depicting all of the possible Lagrange points in the two-body system, right? And I've actually made a list of all of them, right? And these are all the Lagrange points that we obtained analytically. So congratulations, we've obtained all the equilibrium points, and this was just the static case, by the way. So we're yet to deal with the dynamic case. So L1, this is L1, right? Here, it's possibly stable. I don't know, we're gonna have to see that. L2 and L3, right? And L4 and L5, I've positioned them. The diagram is not to scale, but then this gives a brief idea about where these points are and what shape they form, or what kind of polygon looks like, you know, connecting the vertices and, you know, including all of the Lagrange points, right? So that gives a picture of the Lagrange points right there. I hope things have been clear to this end. And now we're going to move on to analyze the dynamics of the problem. Okay. So to analyze the motion near the closest equilibrium point, we're going to have to see what the closest equilibrium point is first, right? And another thing to note is that this time we're considering dynamic equations, wherein the rotating frame velocity for the probe is not 0, right? So we're going to have to consider the Coriolis term. Let's calculate quickly what that is. It's negative 2 times omega across the rotating frame velocity. If we carry out the cross product, we obtain this to be the x and y terms of the Coriolis velocity, right? They're going to be important once we write the force equation. Next, we are going to have to see what the closest point is. Some analysis can, you know, reveal that very quickly, and it actually happens to be L4, right? That happens to be the closest to the second mass. You're gonna have to see something for that, actually, right? Why is it L4 and why is it not L5? So something that gives that away is that so this distance is beta r, which is basically less than r, right? This distance is beta r. And this distance, L4, that's approximately equal to r, by the way. That's approximately very much equal to r, right? This approximately is very much equal to r. So that means that when you're subtracting something that's very small by 1 and multiplying that by r, that result yields something that's very close to r, right? And and when you're adding something that's very small to 1 and you're multiplying all of that to r, that adds something to r, right? So let's say that we've got r to be somewhere around this place, right? Then let's say we've got r somewhere around this place, right? It has to be between L4 and L5. Then subtracting something is going to yield something that's closer to the mass than adding something to r, right? So so that's why I've considered L4 to be the closest point. And L4 is where we're going to expand the Newton's laws, such that we obtain the dynamic equations. So for that, we first write the Newton's law in its full form in the rotating reference frame. So you'll notice that I've included the gravitational accelerations, I've included the centrifugal acceleration, and the Coriolis terms as well, right? So everything's been included in this particular form. We separate the components first of all, right? We separate the components, and we're going to have to expand the force equation near the equilibrium points. So that's what we've done, right? We've split the components first, right? Written the rotating frame acceleration in the x direction and the rotating frame acceleration in the y direction. We've split the components, and we're expanding near x equals x naught, where x naught is the equilibrium point closest to the second mass, right? We've already obtained what that is. And we notice one thing, that we're expanding near that equilibrium point, right? So we can use this linearization formula, right? Because, that small acceleration for that small deviation in x is related linearly, right? And since where we're expanding, there, it is an equilibrium point. We're expanding near an equilibrium point, so that original acceleration is 0. And so that change in acceleration can basically be obtained by the gradient times the change in x, right, near the equilibrium point. So we're basically going to have to differentiate near the x equals x naught point for both x and y components. So I think the mathematics of that isn't particularly difficult. It's just a bit bashy. It's lengthy. I agree, right? So basically differentiate all of this with respect to x, and we evaluate that for x equals x naught, right? We obtain about 1, 2, 3, and 4, 5, 6 terms. Simplifying that, we obtain somewhere around 4 terms. And here, it's actually possible to express all of this in terms of omega, right? If you're gonna ask how, I think it's good to spend some time in analyzing how and why, right? So for the x terms, we're expanding near x equals x naught and y equals y naught, right? Y naught is just 0 because this is an on-axis Lagrange point. Notice this denominator in the first term. So alpha is really small, so we can neglect that, right? Compared to this particular term, we're only keeping the leading order terms as asked in the problem itself. And once we have that, we can also see that in that alpha by 3 to the 1/3, that's also very, very, very small as compared to r. So we're also going to neglect that. And this particular thing, this is almost equal to 2 times omega squared, because that's what omega was, right? Omega, we had something like m1 plus m2 there, right? We had something like m1 plus m2 there. But m2 is like really, really small. So like the leading order is still omega squared there, right? So the first term can be written as 2 times omega squared. The second one is even more interesting because it can be written as 6 times omega squared. And let's see how that is the case. So so for the second term, right? For the second term, we have something like this in the denominator. R and R cancel out. You can work out the mathematics yourself. The leading order term for these two terms is this term. So this term can be neglected. And once you cube that and everything, right, and plug in the value of alpha, right? Alpha is just a factor of m2, right? So alpha was just m2 over m1 plus m2. And notice what happens when you plug this in the second term, right? You basically obtain 6 times omega squared. So that's even more interesting. This is just omega squared, and this is the difference of the Coriolis term, right, due to the velocity in y. So we obtain something very simple for the acceleration in the x direction. We do something similar. We do something very similar for the y component as well. Notice what we're equating for the y component. This is what we're doing for the y component. We obtain something very similar for the y component. You can check out the mathematics. You check out how we differentiated things. You check out how we ignored the non-leading order terms. and we got to the acceleration in the y direction is negative 3 omega squared times the deviation y minus 2 times m times the deviation in the um, x velocity. So I think we're missing a factor of omega here. We're missing a factor of omega everywhere, actually. This is a Coriolis force term. Okay. So missing a factor of omega everywhere, actually. So once we have that, we obtain the differential dynamic equations for x and y completely. We obtain that completely, right? And now we only need to solve this differential equation, plug in the initial conditions in order to get the position deviations as a function of time. So that's all that is required, right? And we assume an exponential solution form, delta x and delta y, to be a times e to the lambda t and b times e to the lambda t for delta x and delta y. And these are basically deviations from the equilibrium Lagrange point, L4. And when we plug delta x and delta y, these solutions, into their corresponding differential equations, we obtain certain conditions that a and b must satisfy. A and b must satisfy along with lambda. And since these two conditions have to be equivalent, that is, they have to yield the same possible values for a and b, right? Their coefficients have to be proportional. These linear equations are the same linear equations for a and b, right? They need to yield the same possible values. So these are identical equations, meaning that the coefficients are proportional. And using that condition, we can actually find what the value of lambda is in terms of omega, right? Which is the angular velocity of the binary star system. So what we basically did is that we assumed for delta x and delta y to be given by this particular form of solution, these two things have to be true. Obviously, they need to satisfy the differential equations. And since both of them seem to be giving values for a and b, their coefficients have to be proportional for these solutions to remain valid, right? These solutions to be remain valid, because both have to be true. And if that is the case, then yes, there do exist values for lambda, right? There do exist values for lambda, which will be given by this equation, in terms of omega, for which these solutions for delta x and delta y will indeed be valid solutions. There do exist values of delta. So there exist values of delta that are positive and negative, right? There exist those values. And there also exist imaginary values once we solve that equation, right? And we lean in more towards the imaginary values of lambda, because if we lean in towards the positive roots, then we'll also get an exponentially growing solution, right? And we don't want an exponentially growing solution, so we're only going to take those values which have an imaginary component. Perhaps we can relate that to Euler's formula and use and obtain a solution in terms of sines and cosines and obtain the oscillatory mode, right? So we're more interested in the imaginary component rather than the real components. So because this is a fourth order equation, we have four roots, right? Lambda can be plus or minus I, root of 2 root 7 minus 1. So those are two possible imaginary solutions, and we also have two possible real solutions, which are these. Right? These are two possible real solutions. And we're staying away from the real solutions for right now. Okay, so because there are two possible values of lambda, there are two possible values for lambda, which will indeed satisfy that these are the solution forms. So since there are two possible values of lambda, then there are also two possible terms that exist in the general form for the solution of delta x, right? Because this is the property of the second order linear differential equations. If one of the terms satisfies the differential equations and another also satisfies the differential equations, because there's a lambda and there's also a negative lambda, by the way, right? There's a lambda and there's also a negative lambda. Because there's a plus I times root of 2 root 7 minus 1, and there's also a negative I omega times root of 2 root 7 minus 1. If there are two possible solutions which satisfy the differential equation, the second order linear differential equation, then a superposition of them will also satisfy the second order linear differential equation. So we use superpositions for both x and y components, right? And the coefficients are arbitrary. They will be determined by initial conditions. So let's try to, let's try to write everything in terms of sines and cosines, right? So lambda, we're inclining more towards the imaginary part. So if we are successfully able to write this like this, then e to the I omega t plus e to the negative I omega t whole over 2, that is going to give cosines and sines by Euler's formula, right? So we're going to have to choose a1 and a2 deliberately, such that a1 plus a2 is 2 times a dash, right? 2 times a dash, because the plus lambda terms have to equate to this, right? And a1 minus a2, that is a1 and this negative lambda term and a2 and this negative lambda term, they have to equal to a dash dash, right? So we're going to have to choose a1 and a2 deliberately so that we can write this delta x solution in terms of this, and that will finally give us this, right? Because those e to the lambda t plus e to the negative lambda t, that is a cosine, and e to the lambda t minus e to the negative lambda t, that is a sine, right? Because lambda is imaginary. We do the same thing for delta y, and I'm not spending too much time in that because it's just the same process. And we successfully obtain the oscillatory mode solutions for delta x and delta y. The only constraint is that when we plug delta x and delta y back into the differential equations which gave birth to them, right, which is this, right? For delta ax, we differentiate that twice, and delta ay, we differentiate that again, the expression for y twice. We plug in the time derivatives by differentiating once, and we basically plug those oscillatory modes in there. Let's let that load for a while. Basically plug in the oscillatory modes in those differential equations which gave birth to them. We obtain something like this, right? We basically plug that in to equations 21 and 22. We plugged in equations 21 and 22 into the differential equations 16 and 17, which are above. We obtain a certain relationship between b2 and a1. And yeah, we also obtain a certain relationship between b1 and a2, right? So so what we did basically is that we basically said that lambda x and lambda y, let's say that they are given by these oscillatory mode solutions. Only oscillatory modes appear, right? As stated in the problem statement itself, the particular solution in which the position deviation grows exponentially, that does not appear. Only oscillatory modes appear. And if only oscillatory modes are indeed to appear, then when we plug these two things in to the differential equation, which gave birth to them, which is this, right? We plug that in, and I've not shown in the mathematics too much of, things being plugged in. Then we obtain a certain relationship, right? We plugged in equations 21 and 22 into the differential equations that I annotated above, and obtain a certain relationship between b2 and a1, and also a relationship between b1 and a2, right? So let's just write everything in terms of a1 and a2. then we obtain something like a complete solution, right, for x and y. And I've dropped the deltas, right? It's just self-understood that x and y are small deviations. So then we obtain the oscillatory mode solutions, right? B1 we wrote in terms of A2 and B2 we wrote in terms of A1 by plugging in those oscillatory modes, right? And you know that A1 and A2 are just determined by initial conditions, right? When you plug in t equals 0, the second term vanishes and only A1 remains, and t equals 0 means the cosine of that is also 1. So the initial position of x at 0 is just A1. Yeah, you plug in the initial position of x at 0 at time t equals 0, you obtain the coefficient A1, right? And since the time derivative of y, right, try differentiating y, you obtain this term to be a sine and this term to be a cosine, and only the A1 term remains if you time derivative it, by the way, right? And when you evaluate that at 0, only the cosine term remains, that is only the term with A1 remains, with something like this, right? It's basically that same constraint that we obtained between B2 and A1, right? So the condition is that the deviation in x has to be related by the with the initial velocity in y with this particular expression. And something similar is also true for y, right? So when we plug in t equals 0 for the initial deviation in y, right, for the initial deviation in y, we see that this term obviously zeroes out because sine of 0 is 0. We see that the initial deviation in y is this, and when we differentiate that, right, when we differentiate the deviation in y, this term becomes a sine and this term becomes a cosine, and only the second term remains when t is plugged as 0. And then we again obtain I'm sorry. So we actually differentiate x, right? We actually differentiate x this time because we're dealing with A2 this time. And differentiating x, right, this term becomes a sine that zeroes out when you're evaluating the initial velocity along x. And this term becomes a cosine, and when we're evaluating the initial velocity along x, only the A2 term remains with a certain factor, right? This factor pops out after the differentiation. So we obtain the initial velocity of along the x direction at time t equals 0 in terms of A2 as well, right? And since equating A2 is A2 from these two equations, you basically obtain the fact that the initial deviation in y also has to be related with the initial velocity in x by this equation, right? So two particular things here. Initial deviation in x has to be related with the initial velocity in y, and initial velocity in x has to be related with the initial deviation in y. Right? Let me repeat that again. Initial deviation in x has to be related with the initial velocity in y, and initial deviation in y has to be related with the initial velocity in x. So these are the two particular conditions in which only oscillatory modes appear. So we've actually solved the differential equations, right, in terms of the initial positions and velocities, and we've also obtained the conditions, because only under these conditions can this particular thing remain the dynamic solution for the deviations, right? Only under this particular condition. And that means that only under this particular condition, which basically were obtained by plugging in the oscillatory mode solution into the differential equations, right? They have to satisfy Newton's laws, right? And they'll only satisfy Newton's laws if and only if the initial positions and velocities are related. These coefficients that determine initial positions and velocities, they're related, right? And those relations, those constraints were enforced on the oscillatory mode of the solutions by Newton's laws, which means if the solution mode is to be oscillatory purely, right, they obviously have to satisfy Newton's laws, and they obviously have to be constrained in initial conditions of position and velocity by the constraints that we just derived here. So these are the constraints. that are required for, you know, the relationship between the deviation in x initial and the initial velocity in y, and the relationship between the deviation in y initial and the initial velocity in x, right? Under these two particular constraints, the solution will be oscillatory, and these are also the constraints that you're looking for, which the fourth part of the problem statement asks. So we've solved the complete um, we've solved everything for x and y in terms of t. A1 and A2 have already discussed how to determine via initial conditions, right? And I think this completes the analysis of the binary stars. So this was a pretty good problem, and it was quite a long problem. It was quite a long analysis, but it did teach us a lot of things. I hope it did. And I hope all of you have a good day. Keep studying physics and keep practicing. Thank you.